Hello students, this is lecture number 36 and we are going to finish the chapter number 9 today. Okay. So, today we will solve problem number 9.4, okay, and which is about this. So, this is a rectangle, this is 2 meter, this one is 1 meter, and there are tractions. So, these are the forces from all the sides like this. Okay. So, similarly here, so compressive in nature from all around, and the value is all T naught. So, this is T naught, T naught, T naught, T naught. T naught is equal to 10 to power 3 Newton per meter. So, not only compressive like this one, there is also force in the other direction as well. So, there is also torsional force, and which is also given. So, force here is given like this, here it is given like this one, here it is given like this, here it is given like this one. Okay. The value of that is also T naught. Yeah. Okay. This is also T naught, T naught, T naught, where T naught is this value, same value. Also given E is equal to 3 times 10 to power 11 Pascal. Poisson's ratio is given to be 0.3. Okay, and boundary condition, essential boundary condition is given UAX equal to UAY is equal to UBY equal to 0. So, basically what it says that at this okay, where ABCD is basically this is A, B, C and D. It says that this point is fixed and this point has a roller support. Yeah, so that means this point B point can move in horizontal direction, but it cannot go up. Okay, so point B can move in this direction, this cannot move, and these 2 points are capable of moving in any direction. Okay, now what do we have to find out? We have to solve the problem basically. So, of course, if you see the degree of freedom here, you will have total is 8. So, 2 here, 2 here, 2 here, 2 here, 8. So, stiffness matrix will be 8 by 8. Out of that 3 is constrained. So, that means we have to invert k, the part of k, and that reduced k will have 5 by 5 dimension. So, this is a problem that inverting k manually may take long time, So, this may be suitable for solving on computer, or manually can be solved, but you have to spend more time in inverting the stiffness matrix. Okay, but still let us see how we can solve it. One thing is you already know how to use what you mean by this rectangular element, and if you know that, we have done already that while solving the 2D heat transfer problem, same thing can be applied. Yeah. Okay. So, as we have done in the last lecture video, how triangular element that we had previously used for a heat transfer problem we actually applied for solving 2D elasticity problem. Also the same kind of thing we will do it today. So looking at this problem, so this is rectangle, so you know that you can actually make a you can first you write the node numbers, and we will place the origin in such a way that this is in the middle, so that it is easy to actually build the shape function. So here we can say this is -1 minus half, right. This will be minus this is 1 minus half, this will be is 1 half, this -1 half. Yeah. So basically what we can also write in terms of A and B basically. So you can say in this case this will be minus A minus B, like this, right. So A B, this means A minus B, sorry, A B, and this will be minus A B, where A equal to 1 and B equal to half. Yeah, so let's write in this way, because we know we have done earlier. So that means general purpose, where you have like this one, and we have like 2A here and 2B here, like this. That the way we have done earlier. Okay, so we know that in that case n1 will be equal to, we know in that case what happens, this we have two lines here, yeah, and this is x equal to A, this is x equal to B. So n1 will be x minus A, x minus B, and here it has to be 1, so it will be 1 over 4 AB. So put for this one, this will be minus A minus B, put minus A minus B, so minus 2A multiplies minus 2B, so 4AB, 4AB by 4AB, which is equal to 1. So n1 will be 1 in this case. So this is n1. Similarly, we can write others as well. N2 equal to, we have n2, so this one here. So x equal to minus A, y equal to B. So x plus A and x minus B. Yeah, and this will be so put the value here, and you get 2A multiplied by minus 2B, so minus, so we get minus 1 over 4AB, and 3 will be equal to 1 over 4AB, x plus A times x plus B, and n4 is equal to 1 over 4AB, and we will have x minus A, x minus A, x plus B, it will be minus. Okay. So that if we put this value minus AB here, so minus A and B, so you get minus 2A multiplied by 2B, so minus 4AB, so it will be 1. So we got all these ends. Next thing is, based on that we have to find out a few things. What? First we have to construct the displacement vector. So let's say displacement vector Okay, so UE will be equal to, and this will be simply looking at this one, this is 0, and our element number is 1, 2, 3, 4. So total is 0 here. In this case, vertical here will be also 0, right, and others. So we can write like this one. So this is U 0, we write 0, then 0, U x 2, then 0 again, because the vertical displacement at node 2 is 0. So 0, then we have U x 3, U y 3, U x 4, U y 4, transpose of that. So we have this 0 given as a essential boundary condition. So we have that. Rest 5 we have to find out. So we have like this one. Now force will have so Fe will have 3 components, we know that, and what is that? One is because of the body force, second is because of the traction forces, and third is because of the reaction forces. Yeah, okay. Now there is no body force. So that means F B equal to 0, basically 0 vector, simply 0. Okay, done. Now next thing is we can have F R, and looking at that, we can wherever we have 0, there will be a reaction. Yeah, so all other, and wherever there is a U, there will not be any reaction. So basically F R will be equal to, you can write it as R R x 1, R x R y 1, 0, R y 2, then 0, 0, 0, 0. So wherever there is a 0 as a vector, there will be a reaction force there. So we are writing those reaction forces here. Yeah, okay. So done. Now we got this reaction force. Now next thing is this one, F, because of the traction we have to find out. So if you look at it, so the traction looks like this one. Yeah, so we have T naught equal to 1000 Newton per meter. So 1000 Newton per meter, and we have both direction. We have like this compressive, and then we have also this shear stresses. Yeah, so negative shear stress, negative normal stress, both we have like that one. Okay, so how to calculate that? Okay, so let's find out. So let's go here. So okay, so let's look at the normal ones first. Okay, so normal we have like this. Okay, so T naught equal to 10 to power 3 Newton per meter. Yeah, and length we have 2 and we have 1 here. Yeah, 1, sorry, this is 1. So basically this is 2A equal to 2, 2B equal to 1, so 2, 1. So total force, since this is all constant, right? So that means we can straight away we write like this. So we have here like, yeah, so just because of the normal, just normal here, right? So just normal forces. So normal traction. Okay, it's normal traction, and because of that we can find out. So see here, this multiplied by this is the total here. So 2 times 10 to power 3 Newton, right? This is, since this is in meter, so we multiply this multiplied by this one, it gives you total force, which is equal to 2 times 10 to power 3, and half of that will go here, half of that will go there, and direction will be like this. So have like this and this, and here you have 2 times 10 to power 3 Newton, sorry, just 10 to power 3, not 2, 10 to power 3 Newton. So total is 2 times 10 to power 3 Newton, half will go here, so hence 10 to power minus 10 to power 3, this is also 10 to power 3 Newton. Okay, similarly here, so this one is 10 to power 3 Newton, 10 to power 3 Newton. Okay, now because of these two, so this done, now this one, so this is the same value as this one, but this is just 1, so that means 10 to power 3 multiplied by 1, so this 10 to power 3 Newton divided by 2, so 0.5, this becomes 0.5. So what do we get? We get 0.5 10 times 10 to power 3 Newton, this also 0.5 times 10 to power 3 Newton. Similarly here 0.5 times 10 to power 3 Newton and 0.5 times 10 to power 3 Newton. Yeah. Okay, done. Now this is because of normal forces. Now because of the shear stresses, now the shear traction. So shear traction is given, which is like this. So here we have this direction, here this direction, here this direction, and here this direction. Yeah. Okay. So we draw here also. So this one is 2. We know this one is 1 from to here. Intensity of this remains the same, 10 to power 3 Newton. So let's draw it here like this one. Okay, now here we have, in this direction we have 2 multiplied by 10 to power 3, and half of this will go here, half this. So that means 10 to power 3 will go here in this direction like this. So we have 10 to power 3, and here also we have 10 to power 3. So half total force, this multiplied, this is length 2 multiplied by 10 to power 3, half goes here, half goes here. So this done. This one is same as this one, but the other direction. So we will have like this one. Yeah. So 10 to power 3, 10 to power 3. Okay, now this done, now this one. Okay, this one is 0.5 times 10 to power 3, which will go downward, here also downward. So here this becomes 0.5 times 10 to power 3, 0.5 times 10 to power 3. Okay, this one here up and up. So we have like this. Yeah. So this is again 0.5 times 10 to power 3, 0.5 times 10 to power 3. Okay. Okay, so now what do we want? We want to add them together, right? So this one is because normal traction, this one is because of the shear traction. So total force, we have to combine the picture, and we have to accordingly draw. So start, so this is 1 2 3 4, 1 2 3 4. So let's draw it, and that way we will actually we will find out what is the total force. So from here, so in x direction we have 0.5 here and we have 1 here, so 1.5. So let's not write, so I will use this one, I will use this one, but I am going to use, I will just write in kilonewton. Okay, so what I mean to say is just I will write here. So this is 0.5 and here 1, so 1.5. So this is 1.5 kilonewton. Okay, then this one. So we have so far, what do we have? So 1.5, this plus this, similarly this plus this is again 1.5. So this is also 1.5 here, here. So this is upward, this is downward. So this is 1, downward is 0.5. So algebraic sum is 0.5, which is upward. So 0.5 kilonewton. Yeah, so 0.5 kilometer, which is upward. This way, if you see here, this way we have 1, this way we have 0.5. So effective this way is 0.5. So effective this way is 0.5 kilonewton. Look at here, this way is 0.5, this way is 1. Yeah, so this is 1.5, 1.5. Now down is 0.5 and this is 1. So 1.5, 0.5. Here we can check out, this is 1 downward and 0.5 upward. So downward will be 0.5. Here to the right 0.5, to the left 1. So to the left it will be 1, 0.5. So the figures in in kilonewton, what you can see is in original picture also it was all balanced. Yeah, so here also it should be. So if you see, these and these are being balanced, and if this is this way, this one is this way, this is towards the structure, this is towards the structure, hence it's a balance. So but this is what the forces are. Yeah, so due to the traction the forces will be these, then these, then these. So these are the components. Yeah, so basically the row number, if you want to write, we can the row number will be this is row number 1, this is row 2, this is row 3, this is row 4, right, this row 5, this is row 6, this is row 7, this is row 8. Yeah, so accordingly we can write. And remember that if it is to the positive x axis, then it is positive. If it is to the negative x axis, this should be negative, and similarly for the y axis as well. So we can write now Ft. Okay, so Ft will be equal to, so we will start, we have 1.5, 1.5. So this is this 1.5, 1.5, and then third is both is positive in this case, positive 0.5. So this also is positive only, this positive and this is also positive, both positive, but 0.5 only. Okay, so 0.5, 0.5. Okay, now third, if you see, this is negative x axis, negative y axis, so both negative, So, minus 1.5 minus 1.5, so minus 1.5 minus 1.5, then we see minus 0.5 minus 0.5 and both in negative direction. So, minus 0.5 minus 0.5. So, we write here minus 0.5 minus 0.5 and this is transpose of that. Okay, and we know that this is in kilonewton. So, 10 to power 3 newtons, we multiplied by 10 to power 3 to all of them. Okay, so we got forces because of this also, hence the total force vector, the F E will be equal to what we said, F B which is equal to 0 plus F T. So, which is given here plus F R, and we will add all together and we will find out this F E. Yeah, so we will see that the reaction forces, for example, F R will have reaction forces here, here and here, and all this will be 0. For F B is 0, F T is have some value everywhere, right. So F R will have reaction forces here, here and here only, and F T has the value everywhere. So basically what we find simply is this will be equal to, we can actually write exactly what we got. We got basically 1.5, okay, plus F R x1, right, 1.5 plus F R y1, then 0.5 plus, right, 0.5 plus F R y2, got it, plus, so we are covered till here. Now we can write exactly like this one. So minus 1.5 minus 1.5 minus 0.5 minus 0.5 multiplied by 10 to power 3 Newton, where we have to basically we have written F R x1, F R y1 and F R y2 are in kilonewton. Yes, whatever value you get, these are in kilonewton only. So this is what the your force vector is. Yeah. So we got a force vector, we understood what the displacement vector is. Now next is the stiffness matrix. Stiffness matrix Ke equal to what? Why we need it? Because we know that this Ke times Ue equal to Fe. This equation we know and we can now solve the problem. I think we used R here for reaction, not the F. So let us write it like that only. So let us make it R, R x1, R y1, then R y2 and so on, where these values, so R x1, R y1 and R y2 are in kilonewton. Okay. So, now the next thing is basically we have to solve the problem, and for solving the problem we need to know the stiffness matrix, and we have to calculate the stiffness matrix. And stiffness matrix, how we know, basically the formula we have for any n noded element, we know what the equation is. So, this is given by simply like this, right. So, this times n b tilde t, then we have d tilde, then b tilde d omega. So, we have to make these things. This is easy, this one d, basically we know what the d is, where d is equal to E over 1 minus nu square 1 nu 0 nu 1 0 0 0 1 minus nu over 2, right. So, this is material property, and this is for plane, right. So, this is a plane stress problem, we can assume that. If it is not given, you can assume. If given, then you have to accordingly assume. Now, this is we have to find out B. So, now we have the value of n that we can use, and we know that B is equal to, so we have like this. So, del n1 over del x 0 del n1 over del y, then we have 0 del n1 over del y, and then we have del n1 over del x, and so on, right. So, we have first we have for 1, then we will have to for 2. So, del n 2 over del x 0 del n2 over del y, and 0 del n 2 over del y del n2 over del x, and so on, yeah. So, so on till what? We have 4, yeah. So, this B will have 3 multiplied by 8 dimension, 3 by 8, okay. So, 2 rows, this is 2 columns for each node, basically, yeah. So, this is 2 node number 1, 2 for node number 2, 2 again for node number 3, and 2 again for node number 4. So, this is how it is. Okay, so this is what the B is, yeah, and then we have D, and if you say B transpose, accordingly we can find, we have like this one. Now, if we have to just find out, let us say K11, so then can we find out? Okay, so one thing is, of course, so we can integrate. So, for that we have to multiply. So, actually what we are going to, how we are going to do is, this will be after transpose, it will be 8 by 3 matrix, this is 3 by 3 matrix, and this is 3 by 8. So, what we get is 8 by 8. So, this will be 8 by 8. Now, if you want to find out just K11, so what I mean to say is, if we have say K E tilde, maybe we can write this is equal to K11, K12 till K18, yeah, and K21 equal to K12, we know that, and so on we write, this is will be K81, right, we have K88, and so on. So, now is it possible that we just find out K11, because if I instead of multiplying like this one, if you can find out K11, in that case we don't have to calculate all of them, but still we know that here that we have to invert 5 by 5 matrix, yeah, because there are 5 free nodes, 5 not nodes, but 5 free degree of freedoms. Yeah. So, so 5 by 5 k we will have to find out 5 by 5 basically the matrix which will be corresponding to the free degree of freedom. Yeah. So, we cannot do it. I mean, you can do it, but it will take a long time. You know, so it's better for for computers basically. So, but still, we want to see that if in the exam if you are asked K11, for example, calculate K11, so can you be able to calculate that? Yeah. So just look at this. So K11 meaning that we have to concentrate on the basically the first row and first column. Yeah. So B is here, B transpose if you do, then this row becomes a column, right? This row becomes another column, this row becomes a third column. So that means this is the which is column right now becomes a row, right? So this row basically, so K11 if you say, then we will have like this. So K11 you have to find out, K11 will be equal to, right, will be equal to this, and we will have the first row of B transpose which will be this one. Yeah. So just we write like this is equal to del n1 over del x 0 del n1 over del y, we write like that. Then we have the D matrix. Yeah. So then we multiply by D. Yeah. Okay. So our D is okay, let's write D like this one, and then we have okay, then same thing we will get here. Yeah. So that means the first row of B transpose which will be like this one, and then the first column of B which is like this one. Yeah. So we will have like this del n1 over del x 0 del n1 over del y, like this D. Okay. So that means we know this value, so we can actually bring this is a constant, I mean it has some constant multiplied by a matrix basically. So let's make it outside 1 minus 1 nu square which this has. So this I am putting outside, and then we will have this. So then there. Okay. And then what we have, we can see here. So let's spell it out. So we have del n1 over del x 0 del n1 over del y, and here we have 1 nu 0 nu 1 0 0 0, then 1 minus nu over 2, right? And then here we have del n1 over del x 0 del n1 over del y, right, and d omega. Okay. Is equal to E over 1 minus nu square. Okay. So I will still write omega. Yeah. So let's say omega, and now let's multiply it. So if you see here, this multiplies this multiplied by this one. So this 0 here make it 0, this 0 here make it 0. So only thing remains here is the first one is del n1 del x. So this multiplied by this one, so we get this one only, so del nx. So let's write this. So del n1 over del x 0 del n1 over del y multiplied by, and this is 3 by 3, this is 3 by 1. So we are going to get 3 by 1. So this will be something like this, and first one we are getting is del n1 over del x. Yeah, this multiplied by this one. Next is this multiplied by this one. So here also we get nu times this one, nu times this one, this 0, this 0. So, just we will get nu times del n1 over del x. Third is this multiplied by this one, so we get just this both 0. So, we 1 minus nu over 2 multiplied by this. So, we get 1 minus nu divided by 2 and then del n1 over del y. Yeah. So, this what we get, and yeah. Next will be just we multiply this and this, and looking at this you see that here there is a 0, so this multiply 0, so this is gone. Okay, so we have del n1 over del x, a square of that, plus 1 minus nu over 2 multiplied by del n1 over del y square. Yeah, so this is what we will get, right? So basically what we get is k11 is equal to E over 1 minus nu square, then this, okay, then del n1 over del x square plus 1 minus nu over 2 del n1 over del y square. Yeah, so and d omega. So we can see that here. Yeah, so 1 minus nu over 2 del n1 del y square here. So this is what it is. Okay, so basically here what we are getting is actually you can expand, we can see, and here it will be E over 1 minus nu square. Here it will be if you multiply here, so will be E, it will be G basically. In this case it is going to be G. Yeah, so E over 2 1 plus nu, so this will be a G value here, and here it will be E over 1 over nu square. But anyway, so this is the what we have to integrate in order to find out k11, and del n1 over del x, how to find out. So we already know that n1 xy is equal to, we have that 1 over 4 ab, and n, sorry, not n but x minus a, x minus b. Yeah, okay, and hence we have del n1 over del x equal to 1 for ab and simply x minus b. In this problem, a is equal to 1, b equal to half. Yeah, okay, so this is because this is 2, this is 1, so length is 2a, has to be 2a, and height is b, which height is 2b, so half, that's why half, so like this one. So we can accordingly find. So this is basically equal to, if you put these values here, yeah, so we get equal to simply equal to 1 over 4 times half and x minus x minus a, y minus b, this is y. So the value get y, so this also we are going to y divided by minus half, basically this is how you get, which is equal to 1 over 2 y minus half. So 1 over 2 y minus half, this is del n1 over del x, del n1 over the del y is equal to 1 over 4 ab, and yeah, and y, so we get x minus a, which is going to be 1 over 2 and then x minus 1. So this is what we will get. Yeah, so k11 that can be calculated now. So k11 equal to, now this will be E over 1 minus nu square, and then now we can have double integral because this is a domain is first we can have integrate in x direction. So, say this one is maybe y direction first, does not matter. So, this becomes minus y minus half to half is b y direction, and minus 1 to 1 is x direction, and then a square of this. The square of this is 1 over 4. So, right here 1 over 4 y minus half square, 1 over 4 this, okay, then plus 1 minus nu over 2, and then del n1 over del n1 over del y, which is this one. So, this becomes 1 over 4 again. So, we write 1 over 4 x minus half square, right, okay, and then we have to close it, and first dy and then dx. So, this is what the k11 will be. Now, it is just a matter of integration, right. You can just now integrate it to find out the value of k11. Yeah, so this is just a one demonstration basically how you can find out k11 individually. It is possible to find out. Now that we know how to calculate k11, so if you have to find out k12, that also you can do it. And how will you do it? So, k12 means we have to use column number 1, column number 2. So, 1 we have to write we will transpose number 1 here, then multiplied by d, and then we will write this. So, this we will take as a row vector multiplied by this one multiplied by this as a column vector. Yeah. So, what I mean to say is if k so k12 will be equal to 1 e over 1 minus nu square this, and then we will have from one side we can write del n1 over del x 0 del n1 over del y. So, which is the first column, the transpose of the first column of the B matrix, and then we have the D. So, okay, so we already wrote here. So, we write it as 1 nu 0 nu 0, so nu 1 0 0 0 1 minus nu over 2, and then we are going to write del 0 here. Second, we have to write the second row. So, let us write like this one, second row or rather second column. So, this is the del will be 0, del n1 over del y del n1 over del x. So, this is what it will be, and dm. Yeah. So, see, so this is the second row of the B matrix. So, let us write here second column, not row but column, second column of B matrix. Yeah, and this is transpose of the first column of the B matrix. Yeah, and hence this will work simply. Okay, now now it remains that how to calculate k1 once we have you know how to calculate, then rest is the algebra that we have done earlier. Okay, now we will spend little bit time on solving a quadrilateral element of any shape basically. So, or you can see the problem, let us say problem 9.3, although it does not tell you to solve it, it is just about the force vector. But let us say in real life you have to solve basically problem something like this one. Yeah, so where it has forces like this. Yeah, this is the T naught which is equal to 6 Newton per meter, whose direction is like this. Then you have 2 0 0, this is 3 1.2 0 4 1.2 1.5, and this is 1 0.6 and 1.5. Okay, so if the shape is like this one, so that means we cannot use the things we have learnt here. So and for that we have to use the isoparametric element. So we have to use isoparametric element. Yeah, which one? 4 noded. So you already know how to do it in order to solve this kind of thing. Yes, force you can do all, you know, like you will calculate what is the length multiply by T naught, and half will go here, half will go here. Why? Because this is constant, okay, the uniform distribution, and direction will be like this and like this one, and hence in order to find out what is the component in this and that direction, so we will take component of whatever we calculated, half goes here, half goes here. Of this we find out the component. So of component will be, we will have, if this angle is, let's theta, so component of this in this direction will be cos this multiplied by cos theta, which will be in negative direction, and this multiplied by sin theta will be like this, which will be positive direction. So we will get the 2 f's here, right. So similarly here you can do it. So force can be done very easily. Only thing is the K matrix, how to find out, and we know that only that K E is equal to, only we know that, right, B transpose D and B and d omega, that we know is still valid here. Only thing is how to calculate B. Yeah. So for that we can use the isoparametric element. Yeah, and we know that any kind of arbitrary element can be basically transformed into isoparametric element, which is like this one. So 1 2 3 4 can be transformed to 1 2 3 and 4. We have xi and the eta system from the xy system. Yeah, and accordingly we can find out the you know that in this case our n1 will be, for example, 1 over 4. So 1 over 4, and then we have xi minus 1, eta minus 1, right. N2 will be equal to 1 over 4, and then we have xi plus 1 minus, we have, and eta minus 1, N3 is equal to minus 1, sorry, not minus, but it will be plus only, 1 over 4, xi plus 1, eta plus 1, and N4 equal to minus 1 over 4, then xi minus 1 and eta plus 1. Yeah. So you have n's, so we have transferred from here to here. So this will be minus 1 minus 1, 1 minus 1, 1 1, and this minus 1 1. Yeah. So we have transformed the axis, and we have like this one, and from there we can calculate the values of what. So we have to find out B basically. So there is a relationship, and we know that what is the relationship. We know that del n1 over del xi okay, will equal to del n1 over del x dx plus del n1 over del y dy. Yeah. Okay. I think we have to write like this one, del x over del xi and del y over del xi. Okay. Similarly, del n1 del eta is equal to del n1 over del x over del eta plus del n1 over del y over del eta. Yeah, and hence what we get is del n1 over del xi del n1 over del eta is equal to we have here del x over del xi. So we write this one, so we have nothing but Jacobian basically coming up here. So del x over del xi, del y over del xi, del x over del eta, del y over del eta here, and here we have del n1 over del x, del n1 over del y. Yeah, so we get this one. Yeah, so basically we know from here that this will be inverse of this. So this we call it j, right? This is j basically. Yeah, so that tells us simply that is del n1. Okay, so let's write in the next page only. So what it means that del n1 over del x, del n1 over del y will be equal to j inverse. Yeah, so this is Jacobian inverse, where this is the Jacobian, so where we can write it j equal to, let's write it here, del x over del xi, del x over del eta, del y over del xi, del y over del eta. Yeah, done. J inverse here, and then we have del n1 over del xi and del n1 over del eta, like this. Okay, so basically we can find out like this one. So this is known, this will we know that j is like this one, this we can find out like this one. Yeah, so we have n1 n2 n3 n4, so we write x in terms of n1 n2 n3 and 4. So okay, so we write we know that x equal to summation of ni xi I equal to 1 to 4, and similarly y equal to I equal to 1 to 4 ni yi. So we know this one, and hence del x over del xi and so on can calculate it, because n is a function of xi and eta, hence we can do it. So same way as we have done for the heat transfer problem, similarly we can do it here. So okay, so the here now we have to calculate B matrix, right? And B matrix is what? B matrix is like this. So B matrix is like this. Del n1 over del x, 0 del n1 over del y, then we have 0 del n1 over del y, del n1 over del x, and so on, right? Then we have del n2 over del x, 0 del n2 over del y, 0 del n2 over del y, and del n2 over del x. Yeah. Okay, so we have like this. Now what happens is we have to construct this one, and how we will do it? We will do it like this one. So first we have to find out del n1 over del x, and then you put it here. We find out like this one, we put it here, and so on. So first we have to find out del n1 over del x. Once we have that, we put this value, we put it here, this value we put it here, right? This one here, right? This one will be here, this one will be here, and so on. And then we construct this E matrix. Okay, so this is a little bit complicated because earlier it was quite easier, because we had in B matrix we just have this one only. Earlier we had in one row we had del n1 over del x, del 1 to n2 over del x, and so on. This row we had, second row we had del n1 over del y, and so on. So we had like this. So in this case, since we have different kind of formation here, so we have no other way. So we have to actually do first we find out what is del n1 over del x, del n1 over del y based on the non things, and once we found out, then we fill and make B matrix, and that's what we can do. Yeah, or in other words, now you know that k11, for example, the way we calculated k11 equal to the way we did, right? We took the first column from here, and then we multiplied by the d, and we found out that k11 was this square plus 1 minus nu over 2 square of this. This was being integrated. Yeah, so so that means that then we can get from here, and then we can put in that integration, we can calculate. Okay, so the bottom line is we cannot put it elegantly, but we can calculate del n1 over del x and del n1 over del y from here, and put this one, construct it, and once we have that, and then we will just use the k, which is ke, which will be equal to this, yeah, b transpose d b d omega, yeah, and this b we have to calculate actually, and then we have to change it to in order to do numerical computation, the integration, then we have to also convert that into a, so basically this is right now xy, this is xy, so we have to convert that in, can be converted into this xi eta form, the way we did in the heat transfer problem, and this will be the same as what we have, like we have to build basically, yeah, from here to, once we build it, we can put it here. So we have this b transpose d b transpose, and then we have j Jacobian. Okay, so Jacobian will come because we are going to write the omega in terms of xi and eta now. Okay, so since we have like this one, and then we can integrate basically. So we can see here that del n1 over del x automatically have xi and eta from here, because these have xi eta, this also have xi eta, hence del n over del x have in xi eta only, or b will in the form of xi eta only. So these all will be automatically xi eta, this also xi eta, and hence we will be able to integrate, right? So yeah, so just to note here, this is a function of xy, and here this will be a function of xi and eta. Yeah, So just to note that automatically it is transformed. So once this value we have the original equation has everything in xy, but once we take value from here which is constructed from this calculation, and this is xi eta, this is xi eta, xi eta, hence b can be written in terms of xi eta automatically, and hence this we have transformed into xi eta. For that we have the determinant of Jacobian here, and you automatically you have everything in terms of xi eta, and you can integrate. You can use your the 2D Gauss quadrature here, and we can do it. Okay, so that is all. I think we have finished chapter number 9. Okay, so I will post the homework now. Okay, based on all these lectures, lecture number 31 to 36. Okay, so in the next video lecture I will start with the last chapter, that is chapter number 10, which is about the beam bending. Okay, so that is all.